Hello everyone, welcome back to Think Sharp Alley, where every turn leads to a smart solution. Hey everyone, today we are starting with Chapter 1, Binary Numbers of Unit 1. But before entering binary numbers, let's take one small step back and talk about something you already know, the number system. Number system is made up of symbols, which we call digits. Now, depending on how many symbols or digits are used, number systems are classified into different types, and the four commonly used number systems are binary, octal, decimal, and hexadecimal. Let's understand this with an example. Binary number system uses only two symbols, 0 and 1. So its base or radix is 2. Now what do we mean by base or radix? Base of a number system tells us how many digits are used in that system. For example, in binary we are using 2 digits, so its base is 2. In decimal, we are using 10 digits, 0 to 9. So its base is 10. So that's why when we write a binary number, we write a small 2 as a subscript, as you can see on the screen, to clearly show that the number belongs to the binary system. Now, for example, 1101 base 2 means this is a binary number. Similarly, the decimal number system uses 10 digits, 0 to 9. So that is why its base is 10. Now in practice, we don't usually write base 10 because decimal number system is our default system. But in theory, every decimal number has base 10.
Now let's see how numbers are actually represented using place values.
Take a decimal number like this. Now we will just expand numbers using place values. So the digits on the left side of the decimal point will have powers of 10 starting with 0, then 1, 2, 3 and 4. And on the right side of the decimal point, the powers of 10 are negative, starting with -1, -2 and so on. So this number can be written as That's it. Next, let us learn how to represent binary numbers. Now here comes the key idea. In binary numbers, everything remains the same, only the base changes. Like over here, the base is 10. So in binary numbers, the base is 2. So instead of powers of 10, we now use powers of 2. So let us take a binary number. For example, this. Again, the powers to the left of the decimal point will be non-negative, starting with 0, 1, 2, 3, and right side of the decimal point, powers of 2 is going to be negative, -1, -2, and so on. Now we'll write it. This brings us to our next topic, converting a binary number into its decimal equivalent. We simply expand the binary number using powers of 2, which we have already done, and then simplify. So 2 cube into 1. 2 cube is 8 into 1 is 8. 2 square is 4. 0 into 2 to the power 1 is 0. 1 into 2 to the power 0 is 1. To the power -1 is 0.5 and 2 to the power -2 is 0.25. In case you have forgotten, let me just remind you, 2 to the power -2 means 1 by 2 square, which is 1 by 4, and that's how we get 0.25. Now adding all of these, I get 13.75, and that is the number in decimal system. So I'll pause here and give you a few binary numbers to try. Pause the video and solve them, and then check your answers with mine. These are for you to try, and let me write down the answers now. I hope all of your answers will match. Now let's move to the reverse process, converting a decimal number into binary. We will start with a simple decimal number without any fractional part. So simple integer, let's say 58 base 10. Now since this is an integer, we repeatedly divide it by 2 and note the remainders and the quotient. What do I mean by repeatedly dividing it by 2? Have a look. So 58 divide 2. Quotient is 29 and remainder is 1. Then we will divide the quotient obtained again by 2. Remainder is again 1. Sorry, in the previous case remainder was 0. Next we'll divide 14 again by 2. So this is what I mean by dividing it repeatedly, that means progressively. And we'll continue this division until the division is no more possible, that means the quotient is 0. So 7 divide 2, remainder is 1. Again 3 divide 2, remainder is 1. Finally 1 divide 2, and here the division is not possible, so I'll go with 2 zeros are 0, so remainder is 1. And this comes to a stop now. The division continues till the quotient becomes 0. Finally, we write the remainders in the reverse order, that is from top to bottom. So my answer over here will be 1111010. Don't forget to write the base radix. Now let's see how to convert a decimal fraction into a binary fraction. That means instead of 58 simple integer, if we have 0.25. How do I convert this into binary fraction? The idea is very simple. Instead of dividing it by 2 like we did for integers, we multiply by 2. So we multiply the decimal fraction by 2 and note the digit to the left of the binary point. What I want to say is 0.25 into 2. So we are getting 0.5, and in the left of the binary point I have 0. So I note that down. So this digit will always be either 0 or 1. Then we take only the fractional part. So over here already this part is 0. So only the fractional part, that is 0.5 again. And again multiply it by 2. So here we are getting 1.0. So this process will continue until the fractional part becomes 0 or it starts repeating. Okay. So here we have got 0, and let us note the number down. Here we have got 1. So since over here no fractional part is left, we stop. And how do we read the digits? In the same order. So 0, 1. So since this was a decimal fraction, so what we have got is also binary fraction. So 0.25 base 10 is actually 0.01. And this is our binary number, so 2. 0.01, this is binary point. So that's it, short and clean. Let us see another example. Let's say we want to convert 0.375 into binary number. So the rule says we will multiply the fractional part by 2 repeatedly until the fractional part becomes 0 or starts repeating. And note the number down to the left of binary point. Important point, do not multiply 1.5. Take only the fractional part. So the fractional part over here is 0.5 and we'll multiply by 2 and not 1.5. Now the fractional part becomes 0, so we stop over here and our answer will be 0.011 base 2. Now here's something interesting. Some decimal fractions do not terminate when converted into binary. So they result in repeated binary fractions. So we will see one such example. Let us say we want to convert 0.427 into binary. So once again we will do the same steps. Multiply the decimal part by 2 and note the number left of the binary point. You can see that the fraction is not becoming 0. So in such cases, we stop after a reasonable number of steps and write an approximate binary value. So that is why here we write the answer. So binary fractions grow much faster than decimal fractions. So even a few binary places give a very good approximation. That's why we don't continue endlessly. Continue until the decimal fraction is eliminated or the binary fraction has at least twice as many places as the decimal fraction. Like over here, decimal fraction has 3 places. So I'll make sure my binary fraction has at least twice the 3 places. That is at least 6 places of decimal. So I've taken more than 6 places. You can see I've taken 8 places of binary point.
Now let's talk about mixed decimal numbers. Numbers that have both an integer part and a fractional part. For example, 36.125, 19.375, 7.33, etc. These numbers are neither purely integers nor purely fractions. Whenever a decimal number has two parts, we treat the two parts separately. For the integer part, we use successive division by 2, and for the fractional part, we use successive multiplication by 2. Then we simply combine both the result. That's the core idea. Now let us move to examples. Let's convert 36.125 into binary. So here the integer part is 36. We will divide it repeatedly by 2 and note the remainders down. Here the integer remainders are read from bottom to top. So for 36, my number is. Now next comes the fractional part, which is 0.125. And now we convert this by multiplying by 2. Note the numbers before the binary point. Fractional digits are read from top to bottom. So combining both the parts, the answer is, we write this part, then 0.001, this one. So left side, divide, right side, multiply. Now you try one more question, pause the video and give it a try, then I'll write the answer. So convert this into binary form. Pause, and the answer is. Now here's something we must remember. Some decimal fractions never terminate in binary. We have seen this. So in such cases, we stop after enough places to get good accuracy. So usually we take at least twice the number of decimal places. So let us see one more example of this type. Let's say we want to convert 7.33 to binary. Now here we have two parts, the integer part, which is 7, and the fractional part, which is 0.33. So here we will divide continuously by 2. We stop, and here we have to go bottom up, and for the next part we'll keep on multiplying by 2. Since it has 2 places of decimal, then I must take at least 4 or more. So I've taken 6. That means we have done enough. So over here it would be, we will go in the same order, that is upside down. So after combining, my final answer would be that's it. Now to convert numbers like, let's say, 10.17 into binary, Again, same goes. 17, we have 1 7 as our fractional part, so it will not terminate. So you will have to stop after enough binary places to ensure accuracy. Now, if the last digit is 0, you may need one extra step. For example, over here, for 10, it is 1010, I already know. You can try. So the answer for this is, and for 17, it will go on. Let's say you decide to keep 4 place, 0, 0, 1, 0. But since the last digit is 0, you need to do one extra step. So that extra step will give you 1, and you may stop over here. So this is our binary conversion. Please check the answer. Do it and check it. So converting mixed decimals is just a combination of two methods. Divide the integer part and multiply the fractional part and join them. That's it.
Alright, that's it for today. Now before you close the video, I've prepared a small worksheet which I'll scroll on the screen. What you can do is pause the video, try to answer them honestly, and the correct answers I'll show at the end of the video so that you can self-mark yourself. Now if something doesn't click, don't carry that doubt forward. Feel free to drop it in the comments. I do read them. And one small request, if this video has helped you understand binary conversion even a little bit better, just tap the like button. It doesn't cost you anything. It just tells YouTube that this kind of teaching helps students like you. In the next video, we will move ahead with addition, subtraction, multiplication and division of binary numbers, where sometimes students get stuck. Till then, keep thinking logically and keep learning only on Think Sharp Ali.